All right, welcome ladies and gentlemen. This is a fairly quick video on some of the basics of stoichiometry beyond using our toolbox. Sort of what can you do with Stoich? What are some typical Stoich problems? This does go right along with your notes, so you want to have those open so that you can write a few things down. Again, stoichiometry as a whole is really essentially just an application of all the different Stoich tools that we talked about. I have not yet seen a Stoich problem that isn't essentially just pulling out one tool from the toolbox after another and knowing when to use them. We're going to focus on three types of problems, but there are many, many more because these three types of problems tend to be the underpinning of a lot of chemistry. So first up is what I call a mass-to-mass problem. Again, this is an application. And this type of problem will give you the mass of one thing, one reactant or one product, and it will ask for the mass of a different reactant or a different product. That's why I call it mass-mass, meaning it gives you the mass of one thing, it's asking for the mass of something else. Now, this is simply just an application of all the tools in the toolbox, and you can solve this by simply using the stuff that we talked about in class. So we're going to be talking about in class brainstorming how to do this problem. So I'm actually not going to tell you how to do this problem in this video. We're going to talk about it in class. But just to see the sample problem right here, this is a very standard mass-mass problem. This is very, very typical. It's a very typical chemistry problem right here. It gives you a balanced equation. That's actually going to be critical. So you might want to think about why is it really important that a mass-mass problem you have a balanced equation. That's super important. It says if 12.4 grams of phosphorus, so 12.4 grams of phosphorus, so this thing right here, 12.4 grams of P4, is burned, what mass of oxygen does it combine with? So it's asking for the mass of this thing right here, the 5O2. And notice that this is in fact burning, so we have the P4 combining with O2 because burning combustion simply means combination with oxygen, but that's a mass-mass problem. It gives you the mass of one thing, we've got a balanced equation, and it's asking for the mass of something else. So be thinking and be ready to talk about how you think we're going to solve this problem in class, because we're going to discuss that tomorrow. So that's just, we're going to save this slide for class, and we're going to roadmap it, and then we're actually going to go through and solve it. And as you might have noticed, there's going to be no calculator allowed on this problem. Yes, we are going to practice doing math without a calculator and doing multi-step math without a calculator. Next up is empirical formula. Now, hopefully this is something that you remember from Regents Chem, because in Regents Chem you are given the definition of empirical formula, and there are always a few questions about it on the Regents exam. In case you do not remember though, empirical formula by definition is the lowest mole ratio of elements in a compound. So i.e., it is when you take the subscripts in a compound, you reduce them all the way down. H2O is an empirical formula because the ratio of 2 H's to 1 O, you can't reduce that down any further. But glucose, for example, C6H12O6 is not an empirical formula because you can reduce the 6 to 12 to 6 ratio down further to 1 to 2 to 1. So empirical formula is the lowest mole ratio. So I want you to stop calling it like the most reduced down version and instead really think of it like this way, the lowest mole ratio, because that's important. You have to understand, like the Stoich tools that we discussed, that the subscripts in the chemical formula represent mole ratios. That's what they mean. So if you think of empirical formula as the lowest mole ratio, well, that's actually really helpful for you. So a typical empirical formula problem, this is very, very standard. So this is not the type of question that you saw in Regents Chem. That's not really what I would call a typical empirical formula problem. It's something instead that you kind of tack on at the end of an empirical formula problem. That's like an addition to stuff. But this one right here is a much more typical empirical formula problem. The composition of adipic acid is 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen by mass. What is its empirical formula? What is the empirical formula of this compound? Again, this is a Stoich problem, but there is absolutely nothing in this problem that is not pulling from the tools that we've already discussed. This problem is simply an application of all the tools we have talked about, and it's about using them, knowing when to pull which one out, and how to use it. So be thinking about that problem. How do you think we're going to solve that? We're going to talk about that in class. We're going to roadmap it. We're going to go through. We're going to solve it. You will be allowed to use a calculator on this. on this one, so we're going to do both types. But just be thinking about that. What if I gave you just, the percent of each element? How do you find then the lowest mole ratio in order to find that empirical formula? And then lastly, limiting reactant. You may or may not have seen this in Regents. Some teachers do it, some teachers don't. But this is going to be a really, really big thing. We're going to see this time and time again throughout the year in AP Chem. Limiting reactant, by definition, the reactant that is completely consumed in a chemical reaction, i.e. the reactant that produces the least amount of product. These two definitions, they really, really go hand in hand. The reason that it produces the least amount of product is because it is the one that gets completely consumed and it gets used up first. So, it gets used up first and then it's all gone. So therefore, you can't make any more product even if you have more of the other reactant. So it's limiting. It limits how much product you can make. It is the limiting reactant. And how to identify limiting reactant problems. This is actually a really key point because an empirical formula problem will contain the phrase empirical formula. They will ask you very specifically, look, what is the empirical formula of this thing? A mass problem will give you the mass of one thing and ask for the mass of something else. So there are going to be sort of two masses that are in play. So that's fairly easy to identify. However, a limiting reactant problem, more likely than not, will not contain the phrase limiting reactant. So that's like a major warning there. It won't identify itself as a limiting reactant problem to you, not in an easy way. So you have got to know what are the hallmarks of a limiting reactant problem. How do you know if you have a limiting reactant problem? Because then that changes your strategy for how to solve it. So how to identify a limiting reactant problem? This is enormous because it's not going to dance naked in front of you. It will not jump up and down and say, I'm a limiting reactant problem. It won't do that. What it will do, I promise you this. This is how you're going to identify it. What it will do is give you the amounts for 2 or more reactants. Limiting reactant problem will tell you, hey, so we've got this reaction A plus B goes to C, and we start with, let's say, 10 grams of A and 15 grams of B. Okay, right, gives you amounts of 2 things, right, gives you masses of 2 reactants. It's got to be 2 reactants. And then it will say how much product is going to be made. So it will ask for the mass of the product. And that is actually how you're going to identify a limiting reactant problem right there. That's enough to ID the limiting reactant problem because it's essentially saying which one produces the least amount of product. Like, we don't know. We've got this much of one thing and this much of something else. Which one is going to run out first? Which one is going to control how much product is made? So that's why that's our hallmark, our identifying factor for the limiting reactant problem. So come to class tomorrow, ready to discuss these particular problems.